Greetings to one and all. This is Sachin SD, first year MSc student from JSS College of Arts, Commerce and Science, Ooty Road, Mysore. So today I am going to explain about periodic table and its elements. So here let us understand what is this periodic table and their characteristics and their properties. So we go by step. At first, let's begin with some basic things about periodic table which we should understand first. So, we all know that matter can exist in the form of elements, compounds, and mixtures. When elements were discovered, a proper classification was required for their earlier and better understanding. So, many scientists adopted different ways to classify them. They tried to find out some pattern or regularity in their properties of elements. So, many attempts were made to classify the known elements from time to time. The earlier attempts are as follows. The first one is Prout's hypothesis, which comes in the year, which introduced in the year 1815. According to this theory, hydrogen atom was considered as the fundamental unit from which all other atoms were made. It is also known as a unitary theory. The next one is Dobereiner's traits, which comes in the year 1829. Dobereiner classified the elements into groups of three elements with similar properties in such a manner so that the atomic weight of middle element was arithmetic mean of the other two. For example, the elements like lithium, sodium, and potassium have the atomic weight. Lithium's atomic weight is 7, and sodium's is 23, and potassium's is 39. When we take the mean of atomic masses, that is 7 plus 39 but 2, we get 23. Similarly, chlorine, bromine, iodine, calcium, selenium, barium are two more examples of such triads. So the next attempt to classify elements was done by British chemist Newland's octave. By this time, 56 elements were discovered. He arranged all these elements in an increasing order for their atomic masses and found that every 8 elements had properties similar to the first. So he compared this to the octist found in the music, and therefore this classification was known as Newland's octaves or the law of octaves. However, this classification had its own share of shortcomings, the main points being that Newlands could arrange elements only up to calcium out of total 56 elements known, after which the elements shown similar properties. So, after the failure of Newland's octave, Dmitry Ivanovich Mendeleev, a Russian chemist, put forward a periodic table that was called Mendeleev's periodic table. Yes. Mendeleev examined the relationship between atomic masses of the elements and their physical and chemical properties. He believed that atomic masses of elements was the most fundamental property in classifying elements. He arranged known elements in the increasing order of their atomic masses and their properties, and thus created a first periodic table containing 63 elements, till then known as Mendeleev periodic table. Mendeleev's law states that the physical and chemical properties of elements are a periodic function of their atomic masses. Here the horizontal rows are called a period. That will be there are total 7 periods in the Mendeleev's periodic table, and the vertical columns you can see here that there are 7 groups you can see you can see this. There are seven groups and sorry, there are seven periods and the total 18 columns are present. Mendeleev periodic table has its Mendeleev periodic table has its own demerits in that no fixed position is given to hydrogen in table as it resemble alkali metal as well as halogens. So this is one of the demerits why we are not using Mendeleev's periodic right now, and there are only 63 elements present in it in his table. Due to these irregularities, a need for a new classification thus emerged. And in 1913, Henry Moseley, an English physicist, discovered that atomic number is the most fundamental property of an element and not its atomic mass. This discovery changed the whole perspective of elements and their properties. Accordingly, Mendeleev's periodic law was modified to modern periodic law, which states that the chemical and physical properties of elements are a periodic function of their atomic number. The periodic table based on modern periodic law is called modern periodic table. Many versions of this periodic table are in use, but the only which is most commonly used is long form modern periodic table. We should now learn in detail about modern periodic table. So let us learn modern periodic table in detail. There are 118 chemical elements known to man. There are 118 chemical elements known to man. This is a large number, and with all these elements combining to make different compounds, understanding them can be very confusing. Here, to the rescue, we have periodic table. It's not actually table, it is tabular arrangement of all the known chemical elements according to their structural properties. Each chemical is arranged in this tabular form so that we can accurately predict the properties of various elements and study the relation between them, and keep a track of newly discovered elements and analyze chemical behavior and how two chemicals might react to each other. An element is a pure chemical substance consisting of one type of atom. Examples would be carbon, oxygen, and sodium or lithium or iron. An atom consisting of fixed number of protons, electrons, and neutrons, which makes each element unique. Protons and neutrons together make up the nucleus of an atom, while the electrons orbit around it. In a periodic table, a chemical element is represented by fixed format. That is, let's take lithium as an example. Here, the atomic number is equal to atomic number. You can see here, atomic number is 3. The lithium's atomic number is 3. It is representing a total number of protons, and the atomic symbol. This is atomic symbol Li, which represents the element's name. One or two letters from the element's name. We can only write 2 as a symbol of that element. So we took lithium, Li, as lithium. So the atomic mass, average atomic mass, you can see here in down 6.941. It represents the number of protons and neutrons. The periodic table can be classified into 3 groups here. And there are metals, metalloids, and non-metals. And other ways to classify elements are like alkali metals, alkaline earth metals, transition metals, lanthanides, actinides, halogen, noble gases. These are the groups which are present in the periodic table. So group 1A, here group, we can see a group 1 where hydrogen, lithium, sodium are present. Alka- Group 1A are called alkali metals because they react with water to form an alkaline solution, which is basic, and they are very reactive. Which one? Group 1 are very reactive, and coming to group 2 are called alkaline earth metals because they are reactive but not as reactive as group 1, and they are so soft metals, they are also soft metals. Coming to seventh group, that are halogens, these need only one electron to fill their outer shell. They are very reactive. These halogens are very reactive in nature. And group 8A are the noble gases, as they have completely filled other cells. They are almost non-reactive. So let us learn about these groups in detail. First, coming to alkali metals, they are group 1 periodic table. They are very reactive, as we know. They are soft solid also. They are readily combined with halogens. They have tendency to lose one electron always, and examples for these groups are sodium, potassium, and cesium. Coming to next, metals. These metals these metals uh, they are very electrical conductivity, high electrical conductivity. They allow electricity to pass through them. They are high luster, they are ductile and malleable. On the left side of the periodic table, they comes on the left side of the periodic table except hydrogen. Except hydrogens, they are all metals. They are usually solids at room temperature. In the room temperature, these metals are solids. Next, coming to alkaline earth metals. Alkaline earth metals, group 2 on a periodic table, are called alkaline earth metals, and abundant metals, they are abundant metals in the earth but not as reactive as alkaline metals. Example for these alkaline earth metals are magnesium, strontium, etc. So coming to non-metals. Non-metals, in the upper right corner of the periodic table, those elements which are present are called non-metals. They are non-lusters, the poor conductor of electricity. They doesn't I don't say that they don't conduct, but they conduct but not as much as metals. mm, some oxygen and chlorine are gases at room temperature. Oxygen and chlorines are present in the form of gases at room temperature. Others are brittle solids. Next, coming to halogens. Group 17 on periodic table are called halogens. They are salt former, combines with a group 1 and 2 to form salts, so they are called salt formers. Ionic bonds, those salts ionic bonds. Examples of fluorine, bromine, and iodine. Next, noble gases. Coming to noble gases, group 18 on periodic table are known as noble gases, relatively invert or non-reactive, gases at room temperature. Examples: helium, argon, rhodium, etc. So next, metalloids. Metalloids, these are the elements that lie on a diagonal line between metals and nonmetals. Their chemicals and physical properties are intermediate between the two. They share properties with both metals and nonmetals. Silicon and germanium are very important semiconductors, and they are the example for metalloids. Next, coming to lanthanides. Lanthanides are the part of the inner transition metals. These are the part of the inner transition metals. Soft silver metals. They are soft silver metals. They are the elements from 57 to 70. Example for lanthanides are selenium and europium. Coming to actinides, they are radioactive elements. They are the part of the inner transition metals. The elements from 89 to 102 are known as actinides. Example for this are uranium and plutonium. So coming to periodic properties and their trends, the periodic properties may be defined as the properties of the elements which are directly or indirectly related to the electronic configuration of their atoms and show graduations. Increases, it may be increases or decreases in moving down a group or a longer period. The common physical properties of the elements are atomic radius, ionization energy, electron affinity, electronegativity, valence electrons, valency, metallic character of the elements, non-metallic character of the elements, reactivity of elements, melting and boiling points of the elements. Let us start with to study in detail about these properties. Let us start with the atomic radius. Atomic radius or atomic or ionic radius is generally defined as the distance between the center of the nucleus and the outermost shell of the electrons in an atom or ion. Periodic trend of atomic radius across a period. As we move from left to right in the period, atomic radius gradually decreases. The reason is, as we move from left to right in a period, the atomic number of the elements increases. So nuclear charge increases while the number of shells in elements remain the same. Examples: exceptional behavior. Noble gases show exceptional behavior. The atomic radii of inert gases suddenly increase as compared to its predecessor, a long halogen atom. The reason for this type of exceptional behavior is that atomic radius refers to van der Waals radius in case of noble gases, while in case of other elements it refers to the covalent radius. So across a group, on a moving top to bottom in a group, atomic radii gradually increases as nuclear charge and number of shells also increases. So let us go with the next thing, the next property, that is ionization energy. Periodic trend of ionization energy across a period is that as we move from left to right in a period, ionization energy gradually increases. This is because as we move from left to right in a period, atomic size or atomic radius decreases while nuclear charge increases. So example for this is exceptional behavior, that is beryllium possess more first ionization energy than boron, because beryllium has half-filled s orbital and more energy is required to remove an electron from off or completely filled orbitals. That is why a noble gas also show exceptionally high ionization energies. Across the group, moving top to bottom in a group, ionization energy gradually decreases as the atomic radius increases. So let's move on to next property, that is electron affinity. Electron affinity or electron gain enthalpy is the amount of energy released when an isolated gaseous atom accepts an electron to form a monovalent gaseous anion. Periodic trend of electron affinity across a period. As we move from left to right in a period, electron affinity gradually increases. Reason, that is, as we move from left to right in a period, atomic size or atomic radius decreases while nuclear charge increases. So, example for the beryllium does not form an stable anion, so it releases less energy than boron on adding an electron, while nitrogen neither releases nor requires a significant amount of energy on adding an electron, so it has electron affinity almost equal to 0. So atom plus electron gives anion plus energy. So this is the basic thing we should understand here. Across a group, on a moving top to bottom in a group, electron affinity gradually decreases here. So coming to electronegativity is the tendency of for an atom of a given chemical element to attract shared electrons or electron density. When forming a chemical bond, the tendency of an atom to attract electron of another atom. Across a period, as we move from left to right across a period, electron negativity increases in the periodic table. Fluorine is the most here we can see the fluorine is the most electronegative element. The reason is, as the nuclear charge increases of an atom, its electron leaving character is also increases. Example for this is, across a group, as we move from top to bottom in a group, electronegativity decreases. So next property, that is valence electrons. Valence electrons is an electron in an outer shell associated with an atom and that can participate in the formation of a chemical bond in if the uh, outer shell is not closed. Across a period, as we move from left to right across a period in the periodic table, the number of valence electron increases. Example, across a group, valence electrons remains constant. It means elements present in the same group have the same number of valence electrons. For example, hydrogen, lithium, sodium elements are present in the one state group and have the same number of valence electrons, which is 1. Valency is nothing but valence is another property where valence is the combining capacity of an atom. It is the combining capacity of an atom across a period. As we gone across a period, on moving left to right across a period in the periodic table, first valency increases then decreases. Example, there is no change in valency across a group. Elements of the same group show the same valency. So coming to the metallic characters of the elements, metallic characters across, as we move across a period from left to right in the periodic table, metallic character of elements decreases. That is because as we move from top to bottom in a group, that periodic table metallic character increases. Non-metallic characters of the elements, that is across a period, as we move left to right in the periodic table, non-metallic character of the elements increases, and as we move from top to bottom in a group of periodic, non-metallic character decreases. Next is the reactivity of elements. Reactivity of elements depends on its electropositive character. So more is the electropositive, metallic character, more is electropositive nature of the element, and more is its reactivity. As its metallic character decreases across a period left to right, so reactivity also decreases. Although reactivity of nonmetals increases on moving left to right across a period, thus we can conclude as we move left to right in a period, the reactivity of elements gradually decreases up to the group 13 and then starts increasing. And coming to melting and boiling points of elements, melting and boiling points of element decreases gradually from top to bottom in a group, while melting point and boiling points of non-metals increase on moving from top to bottom in a group of the periodic table. So here we can see the chart. Ionization increases from top to bottom to top, and electron affinity also increases, but atomic radius decreases from top to bottom. Yes, you can see this. So coming to S block elements, elements of group 1 and 2 constitute S block. In these elements, differentiating electron enters the s orbital of nth. So the general electronic configuration is of S block elements are in ns1 ns1 and 2. Next one is p block element. Elements of group 13 to 18 constitute p block. In this element, differentiating electron enters the p orbital of nth shell. General electronic configuration ns2 and p1. So general characters of d block elements. Before that, we can see yes, some of the general characters of S block elements are: they are soft metals with low melting and boiling points. They are highly reactive metals and providing univalent and bivalent ions by losing 1 or 2 valence electrons respectively. They have low ionization energy. They are highly electropositive metals. They impart colors of the flame. Most of the S block elements impart colors to the flame. They form ionic bonds. So coming to p block elements and its characteristics, general characters, these include both metals and non-metals. They form covalent compounds. They exhibit more than one oxidation states in their compounds, and their reducing nature increases from top to bottom in a group. Their oxidizing nature increases in a period from left to right. S and P block elements are collectively known as normal representative elements. So general characters of D block elements, that are elements of group 3 to 12 constitute D block. In these elements, differentiating electrons enter the d orbit of n-1 shell. So the element with atomic number 104 and 105 were earlier known as Kurchotovium and Hahnium, are now accepted by IUPAC as Rutherfordium and Dubnium. So G12 element, group 12 element, zinc, cadmium and are considered as transition elements, though they are D block elements, because a transition element is defined as the element which possesses at least one unpaired electron in its free state or one of its stable oxidation states. They are hard metals with high melting and boiling points. They exhibit variable oxidation states. They form both ionic and covalent bonds. They are good conductors of heat and electricity. They form colored ions and complexes. Metals and their ions having unpaired electrons are paramagnetic in nature. They act as catalyst. Example: magnesium, cobalt, nickel. They form alloys. Coming to F block elements, these elements in which the last electron enters the f orbital of n-2 shell are called F block elements. The F block elements has two series and each series has 14 elements. These comprise how horizontal series placed at the bottom of the periodic table to avoid its unnecessary expansion. F block elements collectively are known as the rare earth metals. They are also called as rare earth metals. The electronic configuration is n-2 f1 14, as you can see there. And lanthanides and actinides belong to the 6th and 7th period of 3rd group respectively. These elements present between two transition elements, therefore they are called inner transition metals elements. And their heavy metals, they show high melting points and also they exhibit variable oxidation states. They have tendency to form complexes. Their ions and complexes are generally colored, and elements of actinide series are radioactive in nature, and these are called rare earth metals. Elements from atomic number 93 to onwards are called elements from atomic number 93 to onwards are called transuranic elements. These elements are radioactive in nature. That is all about my presentation. Thank you.